Take 3. So we're looking at quenching again in local galaxies, and we have this picture where galaxies start out on the blue cloud. They kind of look like these big, spiral, beautiful disk galaxies, and then some process or processes takes these galaxies, move off the blue cloud, and then they transition through the green valley onto the red sequence. And we see that there's these red and dead galaxies look strikingly different than these blue star-forming galaxies. And the question is, what is the connection between the quenching processes that galaxies undergo as they evolve in this diagram, and does that imprint themselves on the actual structure of galaxies? And so that's what we're looking at. If you go to papers about 10 years ago, you look at SDSS work and you find that, yes, there are hints actually that there is a link between the age of a galaxy and the structure. And so what I'm showing here are plots from Guinevere Kaufman's work from 10 years ago, where she examines the galaxy age. This is parameterized by D4000 in both cases. And she plots 2 different structural parameters. She plots the stellar mass on the left and the effective surface density, which is defined over here. And in both cases, what you see is the existence of a threshold. There seems to be some value of both of these parameters above which galaxies tend to be old, i.e. they tend to be quenched. But what's interesting when you compare these two is that both of these parameters have a fuzzy threshold. I call it a fuzzy threshold. It's not very well defined. There's still scatter, even up to maybe a dex or so in this particular case. And when you compare these 2 particular parameters, they claim that there is actually a tighter relation between galaxy age and structure if you use effective surface density. So somehow the combination of mass and size is somehow more intimately connected with quenching rather than just the total stellar mass. This is seen in more detail. This is work done by my colleague Edmund Chung, who's also a grad student here. He looked at a sample of galaxies at intermediate redshift, and the goal of his work was to try and identify which structural parameter is really the best indicator of galaxy quenching. And so I'm showing you 2 panels here. This is rest frame U minus B color on the y-axis. On the left, we have Sirsic index, which is a global fit, measuring the mass, or the light distribution rather, in these galaxies. And what we see here is that while there is the existence of a threshold, galaxies above Sirsic of, I guess, 2.5 or so tend to be quenched, we do see that it's not a very clean predictor. There are still galaxies that we call outliers. These are galaxies that have high Sirsic, and yet they're still blue and star forming. But Edmund found that if you use a different quantity, he calls this sigma 1 kpc. This quantity is the mass density within a 1 kiloparsec aperture, 1 kiloparsec radius aperture. And when you use this structural parameter, you see that the relation tightens up rather nicely. And so galaxies that tend to be outliers in this parameter fall back into line in this case. And so that suggests that it's really the inner structure that might be really related or is perhaps driving the quenching processes that galaxies experience. Okay, and so there's still several unresolved questions, of course, as galaxies go from here to here. I've been throwing around parameters. Is there a fundamental parameter? Is there a combination of parameters, perhaps, that's best able to trace the quenching state of a galaxy? If we find this parameter or parameters, is there a particular fixed threshold value that's maybe independent of mass or independent of redshift? And finally, the thing that we're really after is what's the actual connection? What's the physical processes that link quenching, which kills star formation, to somehow the distribution of mass within the galaxies? We want to try and understand and try and see if we can find that connection. And so in our work, I'm just going to highlight a few features of our work. Again, this is using local data, so these are taken from Sloan. And with Sloan, we're also able to couple that with UV data from GALEX, which allows us to really resolve the green valley, so all those galaxies that are transitioning from blue to red. It allows us to identify these recently quenched galaxies fairly cleanly. Again, because we have sufficient numbers, we're able to divide our sample into stellar mass bins, which actually allows us to, first of all, take away any trends that might be present, any mass-dependent trends. And it also allows us to identify plausible evolutionary tracks, as we'll see. Again, as we did in Edmund's work, we're using this mass density within a radius of 1 kpc from the center. It's called sigma 1, so you'll see sigma 1 floating around. Again, which allows us to probe really the inner conditions of galaxies, because that seems to be where the action's happening. And finally, one of the benefits of using Sloan data is that we have lots and lots of objects. And so we can actually present mass profiles. So instead of just looking at the central parts of galaxies, we can actually look at the global properties of these galaxies as a function of stellar mass as well as global color, to see if we can get any other handle or insight into the quenching process. Okay, so like I said earlier, our sample is drawn from Sloan. This is now a UV color stellar mass diagram. The galaxies we're looking at are divided into these 6 stellar mass bins here. This is the range in stellar mass. We divide them into narrow mass bins. Again, our sample only includes face-on galaxies. Face-on because we don't want any heavily dust-obscured galaxies that are edge-on that might pollute the Green Valley. We're only focused on central galaxies in this work. So Joanna will be adding to that and talking about satellite galaxies in her talk. And we do impose a redshift limit here. And the main purpose of dividing into mass bins is that we do assume that each of these slices represents an evolutionary path, that the quenching process can occur essentially at fixed mass. So galaxies just move upward in this diagram. Okay, so like I said, we can compute mass profiles using the Sloan data. The way we do that is you take aperture photometry that's available in the Sloan catalogs. They've measured aperture photometry for all these things. You can then convert these light profiles into mass profiles by adopting a mass-to-light ratio conversion, which is what we use. We just take the Sloan measurements and we can empirically derive this calibration, which we apply to the surface brightness profiles and then allows us to compute mass density profiles. And what I'm showing in both of these panels is just a random sampling of blue cloud galaxies and red sequence galaxies. And I'll come back to the apparent differences between those two. Okay, so one of the key results in this is when we examine this parameter, the structural parameter sigma 1. If we plot sigma 1 as a function of stellar mass for our galaxies, we see a clear correlation that pops out at us. And particularly for the quenched galaxies, which are coded as green or red points in this diagram, we see that there's a strong mass dependence, in fact, the power law of 0.64. And so which seems to suggest that galaxies do not quench at some fixed threshold that's independent of stellar mass in this case. It really does depend on whatever stellar mass you are, you have a particular value of sigma 1 above which you can quench. So this is challenging that notion of a fixed threshold. In addition, now if we go back to the stellar mass bins, I was hinting at evolutionary tracks. And so this is a plot showing you sigma 1 now as a function of color, where we divided the galaxies into these 6 specific mass bins here. And if we go with the assumption that galaxies evolve at fixed mass in this diagram, basically we would like to see how do galaxies move in this figure then. Well, it appears that in each of these figures you kind of see a similar distribution, particularly in the intermediate masses. There's kind of this J shape maybe, something like that. And given that, we might claim that galaxies do something like this. They start out in the blue cloud down here, and then some processes over time allows them to grow the inner mass density within the bulge. And then at which point, once galaxies move kind of across the blue cloud, they increase their sigma 1. They reach some threshold value, and at that point, they're able to quench and move upward in this diagram. And so that's our interpretation of looking at this figure here. Okay. So that's looking at the inner parts. We can also, like I said, look at the global structure of galaxies as they quench. Is there something else that we can learn? What I'm showing here are, for 2 of those mass bins, the top row is showing surface brightness profiles again. Now they're color-coded by blue cloud galaxies, green valley, and red sequence galaxies. That's what each of these 3 lines correspond to. And I'm just going to focus our attention on the outer parts here. If we look at the surface brightness profiles, the outer parts of blue galaxies tend to be brighter, maybe not too surprising. These are fairly extended disks. Red galaxies are dimmer in the outer parts. But if we now look at the mass density profiles, and so these are the average mass density profiles for galaxies in those bins, you see something rather interesting. Whereas with light, you see there's a difference. Blue galaxies look brighter. When you look at the mass profiles, you actually see that galaxies, regardless of their color, actually have very similar outer mass density profiles. So it seems that the outer mass kind of remains constant as galaxies quench. But when you look at the inner regions, you see that, in fact, yes, there is a genuine increase in the mass density for quenched galaxies. And so there's this difference here about a factor of 2 or factor of 3 or so in quenched galaxies compared to star-forming galaxies, which is really trying to suggest that, yeah, something with the inner regions of the bulge is really what's kicking off quenching in this case. That's the important thing. Again, but you might have noticed in these particular panels that having a dense bulge is not necessarily, it's necessary to quench, but it's not necessarily sufficient to quench. There's this huge vertical scatter where at a given value of sigma 1, you can have blue things and red things. which seems to suggest that there must be maybe it's a second process that's not directly traced by the bulge or involved by the bulge that is also contributing to quenching. And this is not new. Eric Bell actually made a similar statement in his work. When he looked at Sloan galaxies, he found we're plotting high-surfaced galaxies here, and there's a tail of high-surfaced galaxies that are still blue and star-forming. And so he said, again, that you need something else. A bulge is not sufficient in this case. And so it seems to imply that quenching is a two-step or a two-phase process. You need two things to happen. One, you need to have gas that either needs to be removed, ejected from the galaxy, or somehow stabilized against star formation. And these processes here could do it: merger-driven starburst, AGN feedback, morphological quenching. These things are traced by the bulge or are involved with the bulge. But the second thing you need, the other condition, is that you need to stop gas from falling back into the galaxy, to suppress gas accretion. And this is something that's the popular mode is virial shock heating, and this is something that the halo dictates. So once a halo crosses a certain threshold mass, you can form a stable virial shock which keeps the gas hot. And so the combination of these two processes is apparently what you would need to fully quench a galaxy. Okay, summarizing it all. Sigma 1, which we found, this inner mass density is well correlated with stellar mass for quenched galaxies, which suggests that the quenching threshold is not fixed, that it's not mass independent. Again, if we look at evolutionary tracks at fixed stellar mass, we seem to see that sigma 1 increases within the blue cloud until it reaches a threshold value above which galaxies are able to quench. When we look at the global stellar mass profiles, we see that the outer mass density remains roughly constant for galaxies of all colors, and that the genuine difference in mass distribution is within the bulge. And finally, quenching is most likely a two-step process which requires gas to be removed from the galaxy, something that the bulge can do, and also suppressed. You need to suppress further gas accretion. This is something the halo can do. Okay, thank you very much. Let's see, well, the first thing I would say is that, yes, definitely we should, repeat our analyses both ways, right? We should examine these trends and see what happens at higher redshift and see if they remain this way. That allows us to tackle the redshift stuff. And people have looked at I think Marian Franks did a study where he looked as a function of redshift, what happens, do these thresholds change or not? He would say that, yeah, probably they do, but the thing is that they didn't actually also break up by stellar mass, and so they lumped everything together. And so it would be nice to do a study where we actually do separate both redshift effects and mass effects to see, can we disentangle that? So
let's please just come up to set things up. And so your last point is quenching as a two-step process sounds completely reasonable.
Yep.
But if there was a time scale for quenching, then the surface density would go up, and then it would take time to move from the blue cloud to the red cloud. If that presumably then is not sufficient to explain.
Okay. Could you say that one more time?
So surface density rises.
Yep.
Suppose it takes some time to then become quenched. Just that delay would give you a scatter.
Just like that, yeah, exactly. And so what I'm saying is that here that you do need to have, a high surface density bulge in order to quench, right? But again, you need some second process that, fully shuts down gas accretion onto the galaxy. And so that.
Can't just be a delay. Time scale.
Yeah, and so you're right, it's not just a delay. Well, it's a different process in this case, where we're talking about, let's say it's a halo-related process, right? That would fully shut down star formation, right? And they could happen, you're asking it's a timescale question, right? And so you're saying if they happen on different timescales. Joel wants to get in on this, I think. But
whether it's sufficient to delay or stop gas from cold gas from coming into the halo. That's what the virial shock does. The second question is that enough? In the semi-analytic models that you often don't quench very successful, especially in massive gas, which have lots of gas coming in. Then they also add this so-called radial mode feedback. We don't know exactly where it comes from, but it's basically enough energy being emitted by something to keep the gas from cooling. So you don't prevent the gas from coming in, the gas comes in, it's hot. The problem is you've got to keep it from cooling in order to prevent star formation in these massive galaxies. So do you need that extra feature, or do you think that that's not?
it seems like it would be reasonable to have that. But, I'm sure you were saying?
I think it's the stimulating models.
Yeah.
Okay, we have to move on.